So just a reminder that mean value theorem, let me pull this one over. Alright, so mean value theorem was the main concept that we learned last class. We reviewed intermediate value theorem. The mean value theorem was the main new thing that we had. So let's go back to IVT. Intermediate value theorem, we were required that the function be continuous. And as long as it was continuous on the interval, then we knew that if there was a y value contained within the y values of the endpoints, then that point at which that y value occurred must have been within your interval as well. So that's all intermediate value theorem is doing, is that if our function is continuous, any y value within the interval endpoints must have an x value that's also within that interval. Now, mean value theorem is when we had to start dealing with our derivatives. So for mean value theorem, we have that the function had to be both continuous and differentiable. And for any function that's continuous and differentiable, somewhere within our interval, the derivative equaled the actual slope of the endpoints. So that was our instantaneous rate of change equaled our average rate of change, which was just simply our algebra 1 slope. So the slope using the endpoints. Now, each of these are existence theorems, which simply says that we don't know how many times this occurs, but we have guaranteed that at least once it occurs within that interval. So mean value theorem, it could happen more than once, but guaranteed at least there is one time where your derivative at a particular point is equal to your secant slope. The instantaneous rate of change is equal to the average rate of change, or the slope of the tangent line is equal to the slope of the secant line. So that was the big concept. Now we had a specific case called Rolle's theorem. And Rolle's theorem said, hey, all right, we've got the MVT situation. So it is a continuous and differentiable function. But on top of that, we have also that my endpoints are the same height. And when that is the case, then I have specifically not just that my derivative equals the average rate of change, but at some point in time, my derivative will equal 0. And the reason for that is if my endpoints are the same height, this average rate of change is going to give us 0. So that derivative, since it equals the average rate of change, well, since my average rate of change is 0, my derivative must equal 0 at some point. So Rolle's is just a specific case of mean value theorem. The case where the endpoints are the same, then we know our derivative must equal 0. So those were the things that we learned a week ago. All right, so the first one we're going to take a look at is number 3. Just give me a moment. And I believe number 3 asked you to use the mean value theorem. And as you notice on your homework, sometimes it specifically addresses a theorem, but a lot of times it does not. All right, so number 3, we have a function here, and they tell us it is a continuous function. And it's defined on that closed interval from -4 to 4. They give us the graph, and we've got a line and 2 curves. And it says there is a value within the interval for which the mean value theorem applied to the interval guarantees the value C that contains within that interval, where the derivative equals 3. So again, they're saying mean value theorem applied to the specific interval, so starting somewhere and finishing at 4. If we use that interval there, mean value theorem guarantees that at some point your derivative equals 0. Now again, mean value theorem guarantees that your IROC equals your AROC. But in order for us to use the mean value theorem, we have to have continuous and differentiable. Now we can see that this is a continuous function, but if we look at our graph, we do see there are a couple points where it's not differentiable. What is one point where it is not differentiable? Yeah, at 0, 0. We have a cusp here, so it's going to be not differentiable there. Where else do we have an issue? Yeah, this 0.26. So at x equal 2, there's also an issue of differentiability. So it's asking what are the possible values of A? And A is representing the left end of my of my interval there. So in order for us to apply MDT, we need continuous and differentiable. Guaranteed we've got continuous, but we need to make sure that these intervals will make it so that it is differentiable as well. Alright, so if we used -4, then that would be the interval -4 to 4. So it's saying if A was -4, then I'd have the interval -4 to 4. Well, if I look from -4 to 4, do I have that it's differentiable that entire time? No. So we have an issue of differentiability. If it's not differentiable, then I cannot use the mean value theorem. So I know then that I, the first option, is correct. Alright, so then let's say we choose 0. So going from 0 to 4, again, same thing. On this interval from 0 to 4, will I have that it is differentiable? No, because again, we have this issue here of non-differentiability. So again, for this interval, we would have it's not differentiable. So we can't do that. Now that leaves us with 2, and by process of elimination, we can figure out our answer. But let's double check this. So I'm looking then at the interval 2 to 4. Is my function differentiable from 2 to 4? Now remember, differentiability, we're looking at the open interval. So on this piece here, do I have that it's differentiable? Yeah. So again, when we're talking about differentiability, we're talking about the open interval. So we do have that it's differentiable here, which means we can apply mean value theorem. So let's just double check that mean value theorem actually applies for this situation. Because they said mean value theorem guarantees that the derivative equals 3. Alright, so again, my derivative must equal my average rate of change. So we just need to double check that that average rate of change is indeed 3 on that interval. So my average rate of change on the interval, so we have 12 minus 6 over 4 minus 2. And that gives me 6 over 2, which is indeed 3. So we've got that taken care of, and that leaves us with our answer of 3 only letters. Questions with that one? So mean value theorem, again, must be continuous and differentiable in order for us to apply it in the first place. Here, there are a couple spots where it wasn't differentiable, so we need to choose an interval that did not include. Alright, and then we'll take a look at 7, and if we have time, we'll come back to 8, 4, and 16. Also, real quick, guys, so number 6, when I was comparing my answers with the answer key, I noticed that for number 6, the question asked why there must be a value such that h prime equals 3, but the question has been answered only referring to just h, not h prime. So I believe that this is incorrect here, because they were looking at just the function h, not h prime. So for number 6, what I have for this guy, so if we look at h prime of t equaling 3, then we need to take a look with our mean value theorem. It would say that my instantaneous must equal my average rate of change. So you do want to go ahead and find h prime of x, which requires you to do some chain rule there. Write out what that function is, and then do your average rate of change using the information from our chart here. So we're doing the average rate of change on the interval 1 to 4. So you need to find h of 4 minus h of 1 over 4. And that does show that it is, when you do that, you find that your average rate of change does end up being at 3 there. So we can guarantee that. Okay, that was a side note, sorry. Number 7. Alright, so number 7, it says that we have a twice differentiable function. And they give us some particular information, and they want us to show why there must be a value within the interval -1 to 9, where the second derivative equals 0. Interesting, this number 7 is very similar to number 4, kind of in the general idea of the problem. Let me go and pull it up to work it out. Okay. So it's a twice differentiable function. That means guaranteed we can take the derivative 2 times. So both the derivative and the second derivative exist. So it means by twice differentiable, And again, if our function is differentiable, that automatically means that it is continuous. Alright. And they give us that g of -1 is 9 and g of 9 is -1. Let h be the function such that h is made up of a composition using just g of x. And they want us to show that h prime of -1 equals h prime of 9. And then use this result to show why there must be a value such that h double prime is 0. Alright, so we're dealing with derivatives, so that most likely indicates when we would deal with their mean value theorem. Now, secondly, they're saying, hey, our endpoint heights are the same. And with that indicates Rolle's theorem. And Rolle's theorem says if your endpoint heights are the same, then that means that its derivative has to equal 0 sometime. So if my first derivative has the same height for the endpoints, then its derivative, which would be the second derivative, must equal 0 somewhere within there. So let's go ahead and first show that, and then we can use Rolle's to justify that sentence. All right, so we need h prime. So let's go ahead and find h prime of x. What rule am I going to have to use for the derivative of that crazy thing? I heard one quiet answer. Chain rule, good. So chain rule says derivative of the outside, inside stays the same, times the derivative of the inside. All right. So they want us to show that h prime of -1 and h prime of 9 are the same. So I need h prime of -1. That would be g prime of g of -1 times g prime of -1. And I'm betting that this information is going to come into play here. So g of -1.
Quads, outside trailers, please make sure you exit at this time. There's a fire drill going on. Please exit your facility at this time.
Okay, so number 7, before we were interrupted by fire drill, or lack thereof, of it being a drill, just real fire, I'm not sure. Alright, so we found our derivative for h of x, and now we're evaluating at at -1, and we're going to do it also at 9. Now, they gave us information about g of -1 and g of 9. Sometimes they'll give you information you don't need to actually use, but typically if they give you some information like that, you're probably going to have to use it some way, shape, or form. So please do. Alright, so what did we find g of -1 actually is? 9. So this is really just 9. So what we have then is g prime of 9 times g prime of -1. Okay. And then we have to show that this is the same as h prime of 9. So h prime of 9 would be g prime of g of 9 times g prime of 9. All right, and what do we know that g of 9 actually is? -1. So this is actually g prime of -1 times g prime of 9. Are those the same?
Yes.
All right, so let's actually go and write it to be the exact same so that it truly matches up. I want to truly match up with that. So what property am I using when I rewrite this as g prime of 9 times g prime of -1? Ooh, you're close. Not associated? I muted it. Good. All right, so we just showed that h prime of -1 and h prime of 9 are the same. I'm going to go ahead and rewrite that up there. H prime of -1 equals h prime of 9. Okay, so use this result to show why there must be a value c on the interval such that h double prime of c equals 0. Okay, so we already talked about how this is hinting toward Rolle's theorem, because we just showed that our endpoints are the same heights. And if our endpoints are the same height, as long as our function is both continuous and differentiable, then that means that at some point its derivative will equal 0. Alright, so notice we're dealing with the function h prime. So to check, is h prime differentiable and continuous? Well, since h is made up of a composition of g, h prime is also made up of a composition of g and g prime. And since g is twice differentiable, I said that should say g prime twice. Then we know that its derivative and the second derivative exists. as well as that means that it's continuous. So since h prime is made up of the derivative and the original function, then I know that it is differentiable and continuous because the derivative actually exists, as well as it's continuous. From that information, that's twice differentiable. So, and whoops, we're dealing with h prime. Since h prime is continuous and differentiable, and h prime of -1 is equal to h prime of 9, then by Rolle's theorem, there exists, what letter did they use? C. There exists a value C such that C falls within our interval from -1 to 9, and our derivative at C is going to specifically be 0. And I suddenly changed my function. What should my function actually be? Careful. What are we talking about? H prime. So the derivative of H prime is H double prime. So, because Rolle's theorem says that its derivative would equal 0. So the derivative of H prime would be H double prime. And that is indeed what they're asking for. So this one was actually using Rolle's theorem. Okay, questions on that? Okay. So let's go ahead and move on to our notes for today, which is optimization, which, interestingly, is a lot more algebra and geometry than it is calculus. So I hope you like your geometry things. Usually there are quite a few mixed emotions about that. Alright, so everyone should have received worksheet 5.2. This will be your notes/homework. Is there anyone that did not get a copy? Alright, go and take 30 seconds and read the steps in solving optimization problem. So. Alright, so optimization problems, this is where we are trying to maximize or minimize something. Maximize or minimize. This is a pretty common real-world type topic. You'll notice that the problems vary from things like dealing with in a factory. So, for example, that first problem, where it talks about making sure we have a can that holds its constants but uses the least amount of material. This is ideal for companies to figure this out because then they can save money by using less material. Because we know a 16-ounce can could be a tall and skinny or short and fat. Also, a common type of problem you'll see is perhaps we want a fenced-in area for the cows, or maybe your dog, that is a certain amount of square feet, and we want to figure out what's the least amount of fencing it takes to create that. Again, so we can save the money on that. Or perhaps we only have so much fencing, what's the largest area that I can create with that fencing, maximizing that area with that constant amount of fencing. So those are the types of problems that you'll see encountered. I'm not going to read through these steps since you just did so, and I trust you guys can read. But a couple key things here is that you do want to make sure you draw a picture. Now, I believe for all the problems today, I think there are pictures drawn already for you. But if the picture has not been given to you, draw a picture and label what information you have so you can kind of visualize and see what's going on with it. All right, also it's important to read the problem, probably more than once. All right, so the idea is that we're going to first identify what is it that we're trying to maximize or minimize. That is the function that we'll be mainly working with. And if we think about it, in order to find a relative max or relative min using calculus, what do I have to do to find their max or min? Critical values. And how do I find my critical values? So we want to take that first derivative and set it equal to 0 or undefined. And then what do we do once we've solved for those values? Test it on the number with our first derivative. So that allows us to identify whether it's a max or minimum. Now you'll notice in step 6 it says find the absolute max or min. Absolute max or min, what changes with that is that we have to test the endpoints. You'll notice that for most of these problems, we typically aren't given an interval, so we don't have to worry about those endpoints. But if you are given a specific interval, you do need to also test the endpoints to see do those values, or do those endpoints have higher max or higher y values than your relative maximums or lower values. So just keep in mind if you are given an interval, you do need to test those endpoints with it. Okay, so this is the main thing that we're doing with calculus, is that we're going to be finding whether it's a max or a min and identifying those values for it. That's the extent of the calculus for it. We're doing quite a bit of algebra and geometry with this stuff. The geometry part is sometimes just recalling a formula. Sometimes formulas are given to you, like you can see for number 1. Sometimes formulas are not given to you, as it is with number 2. So you do need to actually recall those formulas that you learned years ago. We will refresh your memory with it, but a lot of times they do give you certain things. Okay, so the idea again is that we want to first figure out what we're maximizing or minimizing, and then in order to find when it is a max or min, we have to take our derivatives that equal to 0 and test it on the number line. That will allow us to identify, hey, when our radius is 5 inches, then I can have a maximum area or something like that. All right, and the final thing that you really want to make sure you do is actually answer the question. This guy here. Make sure you answer the question. Sometimes they ask for that actual area. Sometimes they just want to know the dimensions. So make sure you actually answer the question again. You'd hate to do all the work and lose the point for the answer just simply because you didn't do that last step. Okay. So optimization problems, again, that's when we're trying to maximize or minimize something. And really they're just calculus word problems. But it's not so much calculus. It's a little bit calculus with quite a bit of algebra with it. All right, so let's go take a look at number 1. What are the dimensions of an aluminum can that can hold 16 ounces of pop? Anybody in here want to confess to saying pop instead of soda? No one? I haven't gotten a single student yet to say yes to that. Pop, as some of us call it. Alright, so what are the dimensions of an aluminum can that can hold 16 ounces? So we're required that it holds 16 ounces, but that it uses the least material. And then they give us the equation for surface area and the equation for volume. And they ask us to keep everything in metric units. Alright, so what are we maximizing or minimizing for this problem? The surface area, the amount of material used. So we want to minimize our surface area. Which means surface area is the main equation we're going to be working with. That's the equation we're going to be taking the derivative of and setting it equal to 0. So we want to minimize our surface area. Alright, so let's go and write out what our surface area equation is. So they gave it to us, 2 pi RH plus 2 pi r squared. Alright, and this aluminum can does have both bottom and a top, so we don't have to subtract anything out of it. Now, you'll notice that in these steps, it says that for the example in the steps, they used Q to represent whatever quantity it was you're maximizing or minimizing. So instead of calling this SA, you could just call it Q, but I like to label it similar to what it actually is, what it represents. But if you see Q on answer keys, then that's why they're just calling it Q. All right. Now, if I were to try to take the derivative right now, I have actually two variables that I have within my equation, both radius and height. And that's going to require us to do a lot more work than if we had it in just one variable. So typically, what you're going to do with these types of problems is you want to introduce a second equation that we can then substitute in for one of our variables, so we have our equation only in terms of.
So that means we set the equation of volume to 470.
Very good. So here they actually gave us our other equation. It's not always going to be given to us. Sometimes we have to think about what we know with the problem and bring in that second equation. So we're going to introduce our second equation, which is volume is pi r squared h. And as Nick said, in this particular problem, what must our volume be? Yeah, 470 centimeters cubed. Our volume has to be 470 for this particular problem. So I know my volume is 470, and I have pi r squared h. Now we get to choose if we want to solve for r and substitute it in, or solve for h and substitution. So real quick, just turn to your shoulder partner, discuss what should we solve for and what.
No, we can. Yeah, no, which one's the substitute?
All right, give me.
To substitute into.
Okay, put your hand like this for R, put your hand like this for H. That was really confusing. All right, so if you want to solve for R, if you want to solve for H. Because I don't want you to think that thumbs up then was correct. Okay.
I don't know.
I thought about that too, but okay.
Just like raise your hand.
Did I say this was R?
Raise your hand.
Okay, so I've seen a lot of people say R. So if we solve for R, then we would get, okay, so divide by pi h, divide by pi h. So we get r squared equals 470 divided by pi h. Then square rooted. You guys want to introduce the square root into that? Yeah, a bit of a yikes with that one, right? So let's take a look at if we solve for h instead. So if I solve for h, then I just simply have to divide by pi r squared. So then I get h is equal to 470 divided by pi r squared. A little bit nicer than the other way around. You could have solved for r, you just were introducing square roots, you'd have to deal with the square root and taking the derivative. So that's fine, you're just creating more work for yourself. Alright, so I'm going to go and take this and substitute it in anywhere I see h. This problem I only see at one spot. And now let's write our surface area in terms of just r. So my surface area is 2 pi r times 470 over pi r squared plus 2 pi r squared. Notice now, once I know my radius, I can know my surface area right away. Okay, let's clean this up a little bit. Again, we're aiming to go back to, we take our derivative set equal to 0 in order to find when the minimum occurs. But before we take our derivative, let's clean it up a little bit. So I've got my pi's reduced here. What's 2 times 470? 940. And r over r squared reduces down to what? 1 over r. Now I'm going to go ahead and write that as r to the negative first. I just prefer the negative exponents when doing my derivatives. And then I have plus 2 pi r squared. Alright, so that's my new and improved surface area for it. Now when we go to do our derivative, it's going to be much nicer, much easier. It's just in terms of one variable. Alright, so again, in order to find when the minimum happens, I need to take my derivative set equal to 0. So let's go ahead and take the derivative of this. You can use different notation. You could say SA prime because we're doing the derivative. Personally, I like to go ahead and use this notation because it lets me know that I'm taking the derivative with respect to r. So I'm just taking the derivative of my surface area equation with respect to r. I kind of don't like that there's 2 letters there, but it's okay, I'll whatever. Alright, so taking my derivative, bring down the -1. So I get -940 r to the -2nd. Here I'm going to bring down my 2, so I get +4 pi. Not too bad. Alright, questions so far? What's going on? It's been a little while since we've done derivatives. I think since last year. Alright, so now we're taking... Alright, so now let's go ahead and take our derivative set equal to 0, because again, our mins and maxes come from our derivative being set equal to 0 and tested those twice. So I'm going to set this equal to 0. I'm going to rewrite this. And now we're just going to solve for r. Once I find what that r value is, that is a potential point at which my surface area will be a maximum. Alright, and when I solve, I get 940 over r squared equals 4 r. I'm going to multiply by r squared to get that out of the denominator. 940 equals 4 pi r cubed. So r cubed is 940 divided by 4 pi. And then to solve for r, we're going to cube root both sides. And for sake of time, I'm going to go and tell you what that gives us. This would be a problem in which you would need your calculator. Alright, so when we do that, we get approximately 4.21. Alright, so when my radius is 4.213, then my surface area is either a maximum or a minimum value.
If you don't put the approximate signs, is that going to be correct?
No, you will not lose points for it. It would be improper, but not going to lose points for that. Alright, but again, I need a test to make sure that it truly is a minimum. Because we just found that it's a potential one, now we need a test on the number line to know it really is. So I'm just going to do that off to the side here. And again, I'm testing it in my derivative. And what, 4.213? Alright, so I'm testing it into my derivative. I'm testing it in this equation here. And I'm just going to say, let's pick 1. If I take 1 and put it in, I get -940 plus 4 pi. I'm pretty sure the negative trumps there, so we get overall negative. And I want something to the right of 4.2. I'm going to go with 100. So if I take 100 and put it in, so I get -940 over 100 squared. It's a pretty small negative number. And then plus 400 pi. So positive takes priority there. I went from negative to positive slope. Do you guys agree that is the minimum? Okay. Now, I will say to you that I have not seen AP try to be tricky and give you a value that's not what it's asking for. But part of our checking to see if it's a min or max does require us to test on that number line. So even though it seems unnecessary, please do that extra little check off side just to make sure. You never know what they're going to ask you. Alright, so I have my radius is 4.213, but what does the question actually ask for?
What are the dimensions?
The dimensions. So great, I've got my radius, what else do I need? Height, how do I find my height? Just plug it back into my height equation, right? We actually solved for that earlier. And just a reminder that when we are using our calculator and we get these rounded values, please use the entire value, the non-rounded answer, when you substitute in, which means we should definitely use our store bud. So I'm just going to pull it over to remind us of that. All right. So we had the cube root of 940 divided by 4 pi. Yeah. All right, now here's a really important thing with this. A lot of you will make this mistake, so please pay attention so you don't make this mistake and lose silly points. Notice that I have my denominator sealed in parentheses. I'm taking the cube root of 940 divided by 4 pi. I need to put this in parentheses, because if you don't, then your calculator would read it as 940 divided by 4 times pi. So since this is in the denominator, make sure you seal it in parentheses. If you don't, you'll get the wrong answer. Now, those of you that do have the fancy update, remember you have some fancy options if you do alpha F1, F2, F3. And that first option puts it in the nice fraction form. So you could use that to make sure that you don't type it in wrong without parentheses. Okay, so that's where we got our radius was 4.213. So what I'm talking about with the store button is my H equation is 470 over pi r squared. So I want to make sure I use this full decimal, not the rounded value, because that can really throw off your answer. So I'm going to take this and store it, STO. I'm going to go and store it in for R, just because that's what it represents. You can choose whatever letter you want. Alpha, I think this one's R. Yep. So then when I go to find my H value, I can just type in 470 divided by parentheses pi alpha r squared. One, it makes it easier for typing in 2. Then my calculator is using the full decimal and not the rounded value. And that's where we get our answer of 8.426 or 8.427. AP exam, you can either cut it off at 3 or round it at 3.
Where do we get the R?
What's that?
Where do we get the R?
That was simply from doing the cube root of 940 over.
I mean, the R on the calculator. Like.
Oh, alpha, and then where R is on the keypad. Alright, so then our H value was 8.426 or 427. Okay, so make sure you actually answer the question. It asks what the dimensions are. Typically, answer it with a sentence. The dimensions of the can are, radius is approximately 4.213. What's my units? Centimeters. And my height is 8.426. Questions with that? Liz, go back there. Alright, so again, the big concept, we want to first identify what we're maximizing or minimizing. Take that equation, and we're going to do the derivative, but before we can, we need to introduce a second equation that we can substitute in for one of our variables. So just do an algebra 1 substitution, and then once we've got it all in terms of one variable, take your derivative, set equal to 0, and then you're home free. Alright, so let's go and take a look at number 2. Again, same idea, different type of problem, and probably, well, not more geometry related, it's still geometry related. So we have a cone with the slant height. What is the slant height on a cone? Yes, so question.
What would have happened if once we got R, it was like a maximum, not a minimum?
Then your answer for this would be there is no minimum, or there is no minimum value of material, which, as you can see for this problem, wouldn't make sense, right? There's got to be a minimum value. But if you have that, double check that you didn't do something wrong, but then your answer would be that there's no minimum. But again, I haven't seen AP try to be tricky with that, so first, just triple check your answer. Alright, so our slant height on the cone is this guy here. Alright, and so we have a cone with a slant height of 6 inches is to be constructed. What is the largest possible volume of such a cone, given that our volume is 1/3 pi r squared h? So what are we maximizing or minimizing? Volume. Good, we're maximizing volume. So we want to start off with our volume equation, which conveniently they gave to us, 1/3 pi r squared h. Now, again, we see that we have both r and h. We want to eliminate those variables. They did not give us another formula or equation here. So what else can we introduce in that relates to our problem that could help us eliminate the r or the h? Talk with your shoulder partner. What else do you think we could introduce? Okay, now turn and talk with the people behind / in front of you and share your ideas. See if any of them were the same. Alright, let's go ahead and bring it back up front. Back up front, please. Alright, what else do we know that we could introduce? Who feels brave? No one feels brave. Travis, does that mean you possibly feel brave? Pythagorean theorem, raise your hand if you thought Pythagorean theorem. Okay, some other things I heard was area of a triangle, and I think I heard circle, area of a circle perhaps. Okay, so let's take a look at each of those. Pythagorean theorem, so I'm guessing dealing with this triangle here, we would have r squared plus h squared equals l squared. If I did area formula for my triangle, then I have area equals 1/2 base, which would be r, times my height, which is h. And if I did area of the circle, I would have area equals pi r squared. So these are all things that seem to relate to our problem. But how do we know which one we choose? Well, let's take a look at what information I do have. What else did they give me besides the volume equation? The slant height. The slant height is 6. So from these, I know that I could say for this problem, instead of L squared, in this particular situation, I would have 6 squared for 36. For here, do I know my area of that base? No, I don't know this, and so if I tried using this equation here, I'd be introducing a third variable, which wouldn't be helpful for us. Alright, so down here, do I know the area of my triangle? No, again, we don't know the area of the triangle, so we run into the same issue as that one there. So we do want to go ahead and use our Pythagorean theorem. Notice that we're left with only r and h, and no other variable that we're introducing. So that's what we want to go with. So I'm going to go write that off this side here. So r squared plus h squared is l squared, but again, for this particular situation, we have r squared plus h squared is 36. Okay. So now talk with your shorter partner real quick. What do you want to solve for to plug into our volume equation? Alright, what do you guys think? R squared, and good job catching r squared rather than just r. Since we have r squared in my equation, that's probably going to be the best thing to solve for. If I did h, I'd have to use a square root. Alright, so r squared is 36 minus h. So this, I am putting into r squared. Alright, so let's go ahead and do it. So my volume is 1/3 pi. R squared is 36 minus h squared. Be careful you don't put an extra squared up here. This is r squared we're substituting for, not r, so we don't need squared up there. Come on, be reasonable. Alright, so now let's go ahead and simplify this a bit. I'm going to go ahead and combine my pi and 1/3 together. I'm going to bring my h to this side. Again, what property was that? Commutative. I don't want you guys to get confused with this. Erase that. And let's just go ahead and distribute out our pi over 3h. So we get 12 pi h minus pi over 3h cubed is 1. Are we good with that part? So again, what we've done now is just simply gotten our volume in terms of one variable, because that's what we're trying to maximize. I know I want to do my derivative of that. And we want it just with one variable. Alright, so let's go into our derivative. Again, I'm going to use this notation, dv dh, because I'm doing it with respect to h. So my derivative of 12 pi h is 12 pi. That wasn't so bad. My derivative of negative pi over 3h cubed is minus, let's see, bring down the 3, pi h squared. Still not bad. So again, we've now taken our derivative. We want to go ahead and set our derivative equal to 0 to find what those critical values, potential maxes, and mins are. So we're going to go and solve for h. So I get pi h squared equals 12 pi. Divide by pi on both sides, get h squared equals 12. So h equals, so it breaks down to 4 and 3, plus or minus 2 root 3. So for h, I get two potential answers, a positive 2 root 3 and a negative 2 root 3. So when I go to test that on my number line, again, I'm doing this with my derivative of volume. I'm testing negative 2 root 3 and positive 2 root 3. Now, before we do more work than we have to, let's pause and think about the context of our situation here. What does h represent? Height. So what we just said here is my height could be either positive 2 root 3 inches or negative 2 root 3 inches. What's the issue with that? I can't have a negative height. So what's great with that is I know that I already will not be using that as one of my solutions. I only have now one potential value that could be that the value at which my volume is the maximum or minimum. But we still want to keep that in mind for our number line, because when we're testing numbers, I need something in between these two values. Okay, but I really just need to test the left and right of two groups. Okay, so in between those, let's just go with 0. If I take 0 and put it in for, so again, we're going into our volume derivative. If I take 0 and put it in for h, then I get 12 pi minus pi, so it's overall positive. And what's that? I'm taking, so I'm substituting into my derivative equation, so I'm just testing the point 0. Oh, sorry, I got you, 12 pi, yes, thank you. Alright, so now let's go and pick something larger. I'm going to go with 100. So if I take 100 and put it in, I get 12 pi minus 100 squared pi. Looking like the negative is going to take control there. So we went from positive to negative. And we indeed have that as a maximum. Can we agree with that? Are we all good with that? Okay. So again, just verifying that it's indeed a maximum. So let's throw out our negative. That's just an extraneous solution. It is a solution to our equation, but not in the context of the problem. So we have our height is 2 root 3. Now, what was the problem actually asking for? The actual volume. So if we put into our volume equation, you could actually go ahead and use this volume equation here, since it's all in terms of h. Or go ahead and take h, plug it back in for r, and then go from there. I'm going to do that one because it's actually not too bad. So let's go ahead with this one. So r squared then would be 36 minus, what is h squared? Yeah, just 12. So work smarter, not harder. We simplified here, but look, h squared was just 12. So we get r squared is actually 24. And then our volume equation is not bad. So we have pi over 3 times r squared, which is 24, times my height, which is 2 root 3. And honestly, guys, if this was for response, again, you could have just left it as root 12. That's fine. And if it was for response, we could leave it unsimplified. But it's not too bad simplified. So 24 divided by 3 is 8 times 3 is 16. 16. All right, so the largest possible volume is 16 pi root 3, and what are my units here? Not centimeters. Inches. It took me a while to find it. It says it right here. But it looks like in when you're looking for it. Took me a good 30 seconds. So largest possible volume is 16 pi root 3 inches cubed. And again, you could have used the unsimplified answer, inches cubed. Alright, questions of that? Yes.
If they don't specify, what
You would, if it did not give you any units, you could just say units cubed. Alright. Let's now take a look at our next problem, which actually takes us back to a little bit of algebra, but surprisingly, even though it's a graph, what type of graph is that? Hyperbola, where did that come from? It was somewhere over here. Good job, hyperbola. So hyperbola, but interestingly, geometry is actually the one that sticks its ugly head back into this problem. It's not an ugly head, it's a beautiful head. Alright, so it says find the points on the graph that are closest to the point 50. What are we trying to do? Maximize or minimize? We want to find that which is closest to the point 50. So what are we doing? Minimizing, and what are we minimizing? The distance, right? We're minimizing how far away it is. We want it to be closest. So I'm minimizing the distance from 50 to any point along here. Now we can probably give a good guess. It's probably going to be somewhere around here, right? These ones are not going to be near as close. But we're trying to minimize distance. Alright, so dig deep into your memories. What is our distance?
Yeah, that one.
So I heard square root. Square root is correct. That's the starting point.
Yeah, it's the owl. Yeah, it looks like an owl when you write it.
Alright, it's the owl one.
Am I right or not?
I have no idea. Never heard of this owl. x2 minus x1 squared plus y2 minus y1 squared. Is that the owl one?
Yeah.
Okay, good. It's the owl one.
No, I see.
I can see it. I can see it. So this is the formula. It's a nice effect, yeah. This is a formula that you would be expected to remember and would not be given to you. So make sure you review distance formula. In the stinger, I will show you how we can quickly come up with this from our, because it's really just Pythagorean theorem. Or someone earlier said it's similar to your circle equation, if you remember your equation for a circle, for graph and circle. But, so here's our distance, and that's what we're trying to minimize. So I'm going to go ahead and write that formula down. Now, I do have some of this information here. We're trying to find that it's closest to this point. So we can go ahead and substitute those values in. We know that has to be close to that. And you can use this as either the first point or the second point. It does not matter. Since it's getting squared, it's not going to affect us. I'm going to go ahead and do x minus 5, quantity squared, plus y minus 0, quantity squared. So again, I'm just taking this and putting it into my distance formula. Because I'm trying to find the distance away from this point 5. And we know that y minus 0 squared is just y squared. Okay, so I see that I have both x and y. What other formula or equation can I use to help get rid of one of those variables? The equation that they gave us, right? That graph. And conveniently, that has a y squared within it. So I'm going to go ahead and rewrite this. So y squared would be x squared over 4 minus 1. Now you could get that together as one fraction, but it's really not necessary. Alright, so I have the square root of x minus 5 quantity squared And then y squared is just x squared over 4 minus 1. Alright, so that is my distance that I want to minimize. Now it's all just in terms of x. So we could go ahead and take the derivative as is. That does require us to deal with the square root here. We have kind of a couple options of how we can swiftly move around that issue. So would you agree that I could rewrite this as d squared is x minus 5 quantity squared plus x squared over 4 minus 1? We're good with that? Okay. Now this next part is kind of weird, so listen carefully with this. If I were to do my derivative, I'm doing it with respect to x, right? I'm doing my derivative with respect to x, and it's at this point that I realized perhaps d was not a good choice for variable because don't we write it like this, and then there's a lot of d's happening. But that's okay, we'll manage. So if I were to take my derivative here, I would have to bring down my 2. Inside stays the same, and then technically I multiply it by the derivative of the inside, right? Because I'm doing this with respect to x. The better notation, if it wasn't a d, would be the derivative distance with respect to x, but that looks really weird, so that's why I wrote d prime. So again, technically when I do my derivative here, I have to bring down my power, reduce the power by 1, inside stays the same, then multiply by the derivative of the inside with respect to x. Let me rewrite that as d prime. Okay, so bear with me with that. Let's do the rest of it like normal, works nice and easy. Alright, so my derivative here, bring down my 2.
Good afternoon, Herndon. Please pardon this interruption. Keith Club is hosting a blood drive on Thursday, January 18th. Donating blood can save 3 lives. You can sign up to donate blood at the cafeteria during all lunches, and you must be 16 and older and fill out a parent's consent form. Thank you and have a great afternoon.
Okay, so when I take my derivative here, bring down the 2, inside stays, reduce the power by 1, derivative of the inside is just 1. Bring down my 2, so I have 2/4 x, and then that's just a constant. Now, we're supposed to then take our derivative and set it equal to 0, right? So I want to do my derivative equal to 0. What happens when I take 0 and put it in for my derivative? What does this whole left side become? 0. Just 0. So we really then have 0 is, multiplying that out, 2x minus 10 plus 5x. Then from here we can solve for x. Okay. Now, the other way that you could think of this is if I have, here's my starting point, and I have this distance and this distance. If I were to minimize my distance and distance squared, wouldn't that still give me the smallest value, regardless whether I'm looking at distance or distance squared? The smallest value for distance squared would be the smallest value for distance as well. So you can think of it that way. All right. Your homework is to finish worksheet 5-2. Genuinely try it. Check it with the key. After you've genuinely tried it, come see me with the key.